Okay, hello, welcome everyone. So for today, I'm going just to give you some clarification. It's not supposedly to be formally included in the course, but some of you raised doubts about reservoir simulation that you are not so familiar. So I'm just trying to give you some more information that you feel more confident to see what's that about. And then we are going to go to the part that we left pending last class to see. We said, okay, you told me that I just take one value at the bottom hole, yeah, and then with that I do my calculations, predict my production profile. But really the rest of the system is very important. You intuitively you thought, okay, we are making a very huge simplification. We are just putting one value to simplify everything that is downstream. Okay? And that's really is a very big simplification. We have to see how do we make a better approximation, and for that we have to talk about flow equilibrium. That is one of the fundamental concepts in production engineering. Some other names might be nodal analysis, inflow and outflow analysis, and basically you can resume it to solving a system of equations. But I'm going to try to explain it like in a more intuitive way. I think that's more powerful when you understand graphically what we are doing. And then solving the equations is no problem. You have to find just a way to that they are, don't give you too much trouble, and you use, for example, solver. So let's focus on modeling. So how do we predict? I think that's just too dark. I think reservoir, that's too thin. Okay, you need some tuning. You need some solver to find the right thickness. How do we predict reservoir performance? And when we say reservoir performance, basically what we want is Q of all the phases, oil, gas, and water, versus time. And also we want the flowing bottom hole pressure, okay? PWF. And so I ask you now, where is that pressure? Okay, we have been talking very much about that pressure. So where is that pressure? You know already, for example, that for a vertical well, that pressure, where is that pressure? We have our perforations here. So the pressure is just in front of the perforations. Yes? So that's our PWF. Now, let's say that we are talking about a horizontal well that I have here. Up to here I have the casing, and then I have some open hole section. What will be my flowing bottom hole pressure in that case? I can put it here, okay? PWF, for example. That is representing in a way everything that happens up to that point, and representing that with the famous IPR, okay, that we discussed last class. Q versus PWF. Okay. Or so in the reservoir, okay. So just to clarify that. So what happens if I have multilaterals? Some wells I have not only that, but I have, let me see if I can make a 3D sketch. I hope it doesn't end up too messy. Okay, all of them are in the same plane, X, Y. Okay, so the three wells, the three branches are in the same well. So in that case, you have to define a PWF for each one of the branches. Or you can put in a common point, you can represent them also here. Okay, but you can have a PWF in one for each one of the branches. So just think that it's, really we are saying here that it's a point, but for each well it might be 3 points, or it might be multiple points. Depend on your completion. How is your completion? That clear? More or less? At that point, I just want you to, we are going to have a very short discussion on IPR. later, but just keep that in mind. Okay, when I'm saying PWF, the engineer has they decide in a way where to put it, but it's usually vertical in front of the perforation. If it's horizontal, if it's in the heel, sorry, not in the toe. And if it's multi-branch, you try to make either one for each branch, or you make one where you have the commingling point. So we have three methods to predict reservoir performance, and one of them is material balance, that we have tried last class. That is basically you are assuming that all the reservoir is in a tank, is in a big tank. So it's one-dimensional. We say it's a tank approach. Okay, we have certain tank, and we are assuming also another assumption is that the properties, the tank has some average properties. I'm not making any distinction if there is any change in the vertical or horizontal direction. Okay, the tank has some uniform properties that represent the whole reservoir. Tank approach with uniform properties. Okay, and what are these uniform properties? For example, pressure, temperature, saturation of all the three phases of oil, gas, and water. For example, permeability. What else? Porosity. We assume that the reservoir can be represented by just a tank, and that every time I deplete, the saturation will change uniformly all in all the domain. And you already saw that there is a very big or a very important problem with that approach, that I'm trying to compile everything into one single point. And in the reservoir I might have variation with aerial variation. If I see a reservoir from the top, I might have that one part has low permeability, one part has higher porosity, in one part I have accumulation of water, I have problems of coning. So I have aerial variations, and that's not going to be captured by a material balance. But for our purposes, for field development, sometimes it's enough. You don't have so much information that you can populate a full or more complex model. You have few properties, but you can build a tank model, and that can still give you some very good physical results. Okay. Like I know there is a saying that says better to use a simple model with less simplifications than a very complex model with a lot of simplifications. Okay? So not all the time that you have more complexity is better. Okay? It depends how you populate that model that has a high complexity. It might be that you have a very simple model and you say, well, that might not work. But if it has a limited input and a quality control input, it might still be of better use. And the material balance is basically assuming that, like, I'm not sure if you saw the lecture or you remember the lecture, but you are based on mole. I have certain number of moles, in that case of gas, in a time I. Then I drain those number of moles, or some number of moles, and I end up with Ngi plus 1. And the difference in the number of moles is what I have produced, delta N, in that particular point in time. And now I have moles, but I can convert them to standard conditions. If you remember, we said everything is equivalent. Mass, moles, or standard conditions, everything is the same. I just need some transformation factor between all those quantities. Okay, so that's material balance. Then we have a reservoir simulator. Okay, that the reservoir simulator, I will try to let's make So I have a set of differential equations that they describe the physical phenomena that is happening on the reservoir. And let me see, I found some nice lecture notes from University in Stavanger, I think. Okay, and that's how the differential equation look like. Please don't have nightmares. It's going to be over soon. Okay, so you have a certain set of differential equations, and also you have certain domain, that is the reservoir volume, that you have to. So the idea is first to, so you have, let's put here, you have certain domain, okay, reservoir domain. Then you want to discretize and create a set of sub-volumes. The whole domain, you discretize it and make it in a collection of very small sub-volumes, and that's what we call the grid. Okay. And the set of differential equations on the other side, we also make a numerical approximation of them. This very complicated set of equations usually don't have an analytical solution because they are just so complex, involving too many things, and there hasn't been yet a person that says that's the analytical solution that God gave me. Okay? We cannot do that. So we have to make a numerical approximation. And we end up with a set of algebraic equations and the numerical approximation, if you remember, like for example a derivative of certain property that we can call P with respect to certain variable called X, you have different ways to approximate it, but one way is if you have a grid, okay, Pi plus 1, and you have some distance between them, delta X, you can say Pi plus 1 minus Pi divided by delta X, right? So you convert a very complicated differential operator into something that you can evaluate if you just have the values of the 2 points and the distance between them. And the typical method used for that in reservoir models is finite difference method. Also called FDE. Then you have the set of equations discretized. So let's see if we have from these guys from Stavanger, if they have. Okay, discretized. So you convert the operator. Okay, and there are different schemes depending on how you divide the nodes. So let's put that someplace here. They really wanted to make sure that water is water, okay, that those equations are for water. Just to make a proper reference, I found this on a web, but this is from Stavanger University College, and yeah, I tried to visit the website. I think they changed the link, but the presentation was made by Cyril and Rune Simonsen, just if you want to find it later. Okay, so I have my grid that is just discretizing the volume in blocks, and usually what we use is rectangular blocks. If you have some area of the reservoir that is like that with a very strange shape, you make a bunch of rectangular grids to approximate it. Then you apply, the set of equations are applied on each grid. So at the end, what you end up with these two things is a system of algebraic equations. and we're going to need more space. Okay. You get a system of algebraic equations, and usually I cannot solve, so these equations, they need something, okay? They need two things. They need initial conditions. So that means you need pressure in each cell, and initial pressure on that cell. You need saturations, you need which kind of fluid you have. Okay, this set of differential equations, they are, let me just put it here, flow in porous media, and also you have the fluid behavior, the initial conditions, the saturation, the pressure, and with those things you have at the end, and also you need the boundary conditions, right? What conditions you have. There are some special cells in this grid that have what we discussed last time. We have either a rate or we have either a pressure. So we also need some boundary conditions. Okay, and then I have my, so we call it the customized set of algebraic equations. And really we can have here for any time, for any size between, for example, 1,000 cells all the way to 2 million, 2 billion. I think the current record is held by Saudi Aramco, and they have something like trillion cells. They already passed the trillion cells barrier. But imagine you got, if you took at any point any numerical methods course, if you remember, you usually, for solving this set of algebraic equations, you need, if you remember, you had a big matrix A, you had a matrix called of the unknowns that are X, and a vector called X, and then you had an independent vector called B, right? And we had to solve that system for every time step, Imagine now if the size of that matrix is 1 trillion. If you have 1 trillion cells, you will have 1 trillion the size of the matrix. And then the inversion becomes something that is very heavy, and that you need to find a way to do it very effectively. Solving, and then I have an iterative scheme for solving it in time. And then you obtain all the parameters that you need in time that are rate. So here you get the results that are rate. You have pressure, okay. You have saturations with time, and so forth. That clear? More or less? Now, the nice thing about the reservoir simulator, or the advantages, is that it can be more realistic. I can put really any, in this grid I can populate with any heterogeneity that I see. If there is a variation in permeability, if there is a variation in saturation, etc., I can put it on the grid. So it's really more realistic, and it can capture the complexities of the field, can capture the heterogeneities. But some negative points are, it takes a longer computation time. Also, another complication, that we need a lot of input. Okay, imagine that you have 1 trillion cells. You have to give for each one of these trillion cells many properties. You can assume that they are the same, but if you have any variation, so that's something. Let's say, okay, let's say that we have a reservoir. Okay, just to give you an example, and we had 2 exploration wells. Okay, we made one here and one here, and we found that that one has a higher permeability than that one. So you know in between, you know exactly in this area and you know exactly in that area. But what's going to happen in between of these 2 wells? So you can make all kind of approximations, but at the end you will have to make some assumption that has to be physically based or has to be just, you know, from the top of your head, but you have to make some approximation. So that's one of the deficiencies of Reservoir Simulator, and depending on which stage you are in the development. If it's very early, you have limited information and you have to populate a lot of information that you don't know. So it requires a large input, okay, a high large input. So in early phase, we need to well, not to invent, but we need to extrapolate, or we need to find a way to say how all of that properties require. Okay, but that's just that you know that's something that has become standard in a way. Every time we want to see the performance of a field, we go ahead, run, and try to build our reservoir model. A material balance, I don't think in the North Sea, maybe some few cases, but sometimes it's not so often used. Okay, but I tell you, better to use a simple model with physically correct assumptions than use a very complicated model with a bunch of wrong assumptions. Okay, keep that in mind later. And then we have a third approach that I'm not going to talk about here, but it's called decline curve analysis. That is also called DCA, and that's very much used for onshore US, for fields onshore US, and that basically is using a material balance equation plus the IPR equation plus some empirical information, okay, and I'm going to show you when we arrive to the potential, I'm going to show you just how we derive a decline curve method from all of these equations, okay? But for now, just keep it in mind, something that we use onshore US is very much used, and is in very simply put, okay, you have the rate versus time, and you know your well is declining like that, so you say I have a particular shape, for example exponential. I know that behavior will be C, the Q will be a function, an exponential function with time, or it can be any other kind of function, and that function I'm going to deduce it from these equations depending on which case I have. But just don't be concerned about it, just keep it in your head. There is a third option we don't use too much here in Norway. Okay. So let me here put something that I think was missing from the so on the reservoir simulator there is a high uncertainty in the reservoir, in the subsurface in general. So we usually have, if you more or less let me just pull the picture, it's nice to have a picture. usually I have from the seismic, from geophysical measurements, from the exploration wells, and also getting information from the area, from neighboring fields, from the geology of neighboring fields. I try to make a geological model, what kind of layers I'm going to have in my region, in my particular reservoir. Yeah? And here really comes a tricky part, that I might have different ways that we call realization. Okay, that's one word is used very often, realization. That are different possible explanations of the shape or the structure that I might have in the subsurface. And that really creates a problem, because at the end what we want to compute for each one of them is the TRR, for example, the recovery factor, the rate versus time. And what happens now if we have, you're staying too still? I have to wake up sometimes. That's not helping with the, okay, to help you go to sleep. Okay, so that really doesn't help, because we have to have them track if all of them are feasible, because from that geological model you start to populating with some properties of the layer. First you try to make build layers, and then you try to populate information of the rock in each one of those layers, and from there you create your reservoir model. You do the gridding and you assign properties to each one of these grids. So that's more or less on that, in a very simplified way. Okay, that's the workflow to create reservoir model. Yes, but the problem is that we might have different alternatives. And not only that, but within every alternative we might have, like I told you, we measured here, but we don't know exactly what happens in between, right? So that's uncertainty, and I told you how do we manage it in decisions, in economy, in reserves, but we really haven't talked too much about that. So I will just mention a few let's see. Okay. So there are three ways to address uncertainty. That will be uncertainty in the creation of the subsurface model. Okay, that, remember, keep in mind, is very important, because it tells you revenue versus time. It tells you how much do I have in the subsurface, and it tells you how much I can recover. What will be my ultimate recovery factor? So there are three ways. One of them is create so try to define the most likely of all of these realization, to define the most likely realization. Define a base case. The most likely realization. Okay. And you might have arguments for why to go for one or the other, but basically you choose one that really you trust your geologist, that's the best representation, and then you run sensitivity analysis on that case. Okay. Remember, put plus or minus if there is any variation of permeability, there is variation of saturation, there is variation of the length. You start, but all of them anchored on that base case that you think is the most likely case. Then another way is to define a limited number of cases, and this is typically between 4 and 5. Okay, sometimes can be 3 or 2. That's all the. Okay, and then you run sensitivity analysis on each one of the realizations. So, and we also have to assign, if we define cases, okay, we say it could be like this, could be like this, could be like this. We want to associate our probability to each one of, just like we did in decision trees. Okay, so we have to assign a probability to each case. Yeah, and that's a bit tricky to, that depends on the, okay, we can say here, so how do we do that? It's not simple, and I don't have a solution for you, but actually we ask the expert, that is a guy with glasses and a beard, okay, that who usually makes a bunch of money, okay, and usually maybe has the hair like that, and you know, he is the expert, so he's going to tell you which one is more likely to happen. And then there is, so that you're increasing the complexity, okay? Here, that involves some work, not much. That involves a lot of more work, because you have 4 cases and you have to run all the sensitivity for each one of these cases. And then you have the final extreme, that is, what have we used for the reserves, if you remember? Monte Carlo, yes? So you run what they call stochastic model, and compute the most likely outcome using Monte Carlo, or any other method, like we saw this, if you remember the name, hypercube, Latin hypercube sampling, was that the name? Sampling, okay. And this sounds really, that's what we really will desire, right? To try to see really each one of these positions in my reservoir can have certain distribution, and I can select one randomly and then run the simulation, get the result, and then run it again with multiple times. But you saw already we had only how many? 5 variables, and we had to run 8,000 iterations. Imagine now that we have 1 trillion cells. We have, for each one of these cells, we have maybe 10 properties, okay? And how many cases I will have to run to get some okay, I will be in a very high number. So this is usually not, I do it for only a few properties. Okay, I don't do it for all of them. So I try to lock some properties that I'm sure they won't have any variation, and I make the change in the rest. But just keep in mind, this is a very computationally expensive process. Due to the number of cells and variables per cell. So it almost all the time, if I want to run it on the full model, it's just too expensive. I cannot afford it unless the model is relatively small. Yes? Okay, so just to give you a flavor, Reservoir Simulator plays a central part. You had already a kind of a proxy, and you understood more or less how it works, but we are not going to cover it too much in this course. Okay, any questions? No questions? Okay. Now let's go to the main question we want to answer here is how to capture properly the pressure required at the bottom hole to flow to the processing facilities. Okay. You know, we have a very complicated system after that I want to be able to quantify, just like in the same way we have done the performance of the reservoir, we want to quantify what is the performance of the rest of the system. And I told you that there are two so that analysis, just, you know, keep in mind the reservoir analysis, we are making changes in time, okay, and we are producing in time. That analysis of the back pressure, if you remember from last class, we were doing it at one specific point in time. So anybody can say why these two discrepancies? Why we do one analysis over time and the other we say at one particular point in time? Any idea? You assume, okay, if I have, for example, the evolution of my reservoir pressure versus time, that the change, for example, in the time frame of operations, that the change in reservoir pressure, for example, in 1 week or in 2 weeks, really is not much. So I can assume that that's a kind of a pseudo steady state condition. Okay, not exactly steady state, because we know it will change by the end of the week. It won't be 270.1, but it might be 270.08, maybe. So there is going to be a change, but in that particular time frame, I can say, I can assume that it's relatively constant. That means I can assume what is being delivered from the wellbore is constant. Okay, what you say, the IPR is constant. So here we come to this concept of flow equilibrium. And let's make, you know, our production system. So we have a well, we have our Christmas tree that you already know how we call all of these valves. How do we call them? Yeah, that's the wing, secondary wing, and master wing. Okay, and the secondary wing we can use it for many things. But, so you were not sleeping on that class on the architecture. That's good to hear. Okay. In that system, we can detect, first I want to call your attention to two things. One of them, we have two very clear bounds. Okay? One of them is reservoir pressure, that we already, by this argument, that the change is very, very slow, so I can assume really in 1 week it will remain more or less constant, for example. So I have that pressure in one bound, which is constant. And then I have that pressure on this bound that is constant also, right? So how do I keep separator pressure constant? I think we talked about it before. What two elements that the separator has? Two controllers. Level controller. We had that discussion before, right? Level controller and pressure controller. So it doesn't matter what comes to that separator, it will try to adjust the two valves such that you have all the time the same pressure. So those are the two limits, or what I call the bounds of my of the rest of the system that I want to study. Okay? That clear? Okay. Yes, I think we can take a break now and we come back in 15 minutes. Yes? We continue. Okay, so first, just to to recap. So we are now interested to see what is the back pressure that we need, okay? Or in another way, we want to model or represent the rest of the system in a better way. Not just using a single value of pressure, but see how the rest of the system behaves. And I told you already, so we have two bounds, okay, two pressures, and all of this part we represent it usually with an equation called IPR that I already mentioned to you. Looks something like that: PWF versus rate, and it looks something like this for liquid. Okay, that means undersaturated oil, and it looks something like that for gas or saturated oil. Very simple. You're trying to, and if you see when I have no flow, the rate is 0, then that pressure should be reservoir pressure. And you get the impression if I produce from that volume, from that reservoir, then it's going to decline with time and the IPR is going to change with time, probably becoming smaller and smaller and smaller. Now to address that problem, I think we can go first to one very simple example with a pipe. Okay, so imagine now, let's change, before going to this complex system that has many parts, that has many components, let's change and look to a very simple system, which is a very simple horizontal pipe. And in this pipe, let's say we have is horizontal, we have single phase, we have a phase circulating through it, Q and P2. So we have 3 calculation ways that we can calculate that pipe. Okay, we have the first one, that is I'm going to call it available pressure at the exit of the pipe. And that means I provide P1 and Q, and I calculate P2, right? All of you can do it. All of you took a basic course, a single phase flow in pipes. Some of you in process settings, some of you some other course. But you can say, if I provide those 2 conditions, I can calculate what will be the pressure here, right? No problem. So now I'm going to ask you one more question. How does it look like if I plot now, I try with different rates, but P1 is constant? How P2 will look like? So let's start with what we know, 0, okay? If the rate is 0, how should be P2? Equal to P1, right? So I'm going to put it here. Now, if I start increasing the rate, what will happen with P2 compared to P1? Will it be bigger or will it be lower? Should be lower. Why is that?
Pressure drop.
The pressure drop, but remember, specifically the pressure drop has the pressure drop I can divide in delta P by friction and the delta P by gravity. So if this one is 0, because I really don't have any change in elevation, that one is a function of rate. If I increase the rate, it will be greater and greater and greater. So that curve is going to look like that. All of you agree? Yeah, it's going to go like that. So that's first note. This curve is calculated with the current, co-current. I'm calculating pressure drop following the current at every position. Okay, so that's the co-current pressure co-current calculations, and that's also the available pressure at the discharge of the pipe. So I'm going to call it the available pressure curve. Also, we can call it, if we are using some more economical terms, we can call it supply. So that's very clear. That's the first calculation method that I have. Then I can also calculate the required pressure at the inlet of the pipe. That means I provide P2 provide Q, and then I can calculate the pressure at the inlet. That I know I can also do, right? So let's try to make again the same plot. Rate 0, and here I'm saying P2 equal constant. So how that curve is going to look like? Okay, 0, it should be equal to P1, right? So sorry, P1, so here I'm plotting P1, so it should be equal to P2, right, because I have no flow. But then when I increase the rate, I have the frictional pressure drop. So let's put it here, P1 minus P2 equal to delta P. So I'm now clearing P1 is equal to P2 plus delta P. When I have no rate, that is 0, so P1 equal to P2. But when I have a rate, that one increases, so I all the time have a value greater than P1. So that curve looks like that. All of you agree? Yes. It's the same curve, the same pipe, the same system, but I'm looking from the end and I'm looking from the inlet. Yep. And you will see right why just to make a point. And that curve is calculated counter current, because I'm going against the flow direction. So I calculate pressure drop until I finally reach here. And it's the required pressure at the inlet of the pipe. And there is a third way that I can use, that I can calculate the rate. That means if I provide P1 and P2, I can calculate Q, right? Yes? And that is more or less, so if you see in that system, that has to do also with the bounds. Okay, I have here 2 bounds, and I want to calculate the rate. Okay, what happens if I don't have any of the bounds? Can I calculate the rate if I don't have that pressure, for example? I need something, okay? I need either to fix rate and one pressure, I need to fix the 2 pressures, or that pressure and the rate. Yeah, to solve the problem. Now I'm going to ask you, okay, a tough question. In the reservoir simulator, we already said we put a pressure condition here, right? So what is the other bound, the other pressure? We say intuitively we need either 2 pressures and we calculate the rate, or we give the rate and we calculate the pressure. but in this case we are providing here just one pressure, right, in the well. So how do we close the equations in that case? So first, just one question. What is the question? What is the condition that I'm applying in all of these walls?
No flow.
No flow. Okay? Something very important to remember. In all of these, I have to apply the condition that there is no flow coming in and out. Otherwise, these equations that are applied in these boxes are hanging. They have too many unknowns, more unknowns than equations that I have. And then the other thing is that each one of these cells, they have a pressure. And that's really the difference. What is driving the fluid towards the well is the pressure in the neighboring cells towards the pressure of the well cell, the cell of the well. Okay? Okay, now we have these two, and I have been talking here about a piece of pipe. Okay? But I can really use these two curves, the available and the required, to characterize some more complex part of the system. For example, let's take a look at this part. Okay? Okay? So how are we going to characterize that part? So let me maybe just make a trick. Okay, so I can use the available and required pressure curves to characterize complex part of the production system. Because you're saying, okay, that's okay, but that's a case we really know is trivial. It's a horizontal pipe, I have single phase fluid. It's something that I already know. Here you're talking about something much more complex. So how this very simple principle can apply to that very complex situation? And that's what we are going to try to find out now. So that system, first, what do I have here? First I have, in the reservoir, I have flowing porous media, right? And I have also a change of phase, probably. Okay, so I have fluid behavior until I reach to the bottom of the well. Now, in this section, all the way to the wellhead, that I will put the point here, wellhead, what do we have? We have flow in conduits, okay, in a piece of pipe, and that flow of conduits. So what do I need to compute the pressure drop of these flowing conduits? I need a pressure drop model. That might be just like I told you before, delta P friction plus delta P gravity. I need, remember also the temperature is going to change when I'm going all the way to the surface. So I need also a temperature drop model. And this pressure drop has to be not only single phase. I might be that I have just gas or oil, but I might have also more than one phase, multi-phase. That in the pipe, if I make a zoom and I look in detail, I will have actually, for example, some droplets of gas inserted in the liquid, or the opposite. I might have a film of liquid and some gas in the center, for example. And that's very different from single phase flow. So that I have to be, depends on what I have. And then I need something else that is the fluid model. That's going to tell me how some properties of the fluid fluid properties change with pressure and temperature. Okay? But what I'm going to tell you now is a big truth. No matter how complicated, how difficult these models are, how it's going to look, the available pressure at the wellhead. If we make the analogy with the other case, imagine that that's just a piece of pipe, the same piece of pipe that I'm entering with PR and I'm calculating PWH. How PWH is going to look like versus rate. First, which case is it from the three cases that we analyzed? Is the available, the required, or is the delta P? Okay, if you see, we have P1 is given, P2 is what I want to calculate, and I want to change the rate. So it's number 1. So that means that the wellhead pressure should look PWH versus rate, and remember this is the rate, the surface rate, and for here, for simplicity, I will use of the preferred phase. Okay, that might be oil or gas. So the wellhead pressure is going to look, is the available pressure curve, so it's going to look something like that. Okay, a monotonous, continuous descendant curve when I change it with rate. That means, and that makes sense, if I want to produce more and more fluid out of the formation, I will have to put a lower and lower pressure at the head of the well, at the wellhead, right? That makes sense. Yep. Now please note that I can make that point not only at the wellhead, but I can put it any place in the system, any place that I want. For example, here, I can put it here. What happens if I put it here in PWF? What do I get? The IPR, right? And the IPR looks like that. Yes? Okay, so that confirms our theory. Now let's go to the rest of the system, to that part, and I have an advantage. You will have to run a bit to make the drawing. Now looking at the rest of the system, okay, so this system seems similar to what? Okay, if you remember our pipe example, we had P1, we had P2, and we had the rate. So it looks like exactly our second case, the required pressure curve, right? I want to calculate the pressure at the wellhead, that is exactly the same pressure that we were discussing before, and I have a fixed pressure at the exit of the pipe, separator pressure. So that is going to look like something like this. Okay. Now I'm asking you, that system, could it have different equilibrium rates, or should it have only one unique rate? Okay, I'm not touching anything. I go connect the well to the separator, and it starts producing. I'm not touching anything on the system. Should it have multiple rates? No, it should have only one unique production rate, right? That's what it makes sense. Now you're saying, but you're giving me two curves with two possible rates, that curve and that curve. So how, the only way that the pressure, and it's the same point, okay? So the only way that the two pressures can be the same is in the intersection, right? So if I say the only feasible operating rate is the intersection of both curves. Okay, so if I bring that one down, let's see, and I bring this one here. Oy. Okay, and that I say just exactly like in economy. Okay, that will be my supply, that will be my demand. The operating rate, the wellhead pressure should be unique. I should have only, if it's the same point, 1 millimeter to the left, 1 millimeter to the right, it should be equal, and that's how I find my equilibrium rate, the rate at which the system is going to operate. That clear? Yeah. You think this is trivial, but the thing is that in the field you will find more complicated versions of that curve, different models, different measurements that don't make sense, and if you don't have this simple concept clear, it's going to be very difficult for you to understand the equilibrium of the system, at which rate you're going to be operating. Okay, so we have to make the intersection, right? So now let's try to put some equations to this problem. And for that, so we now have the IPR equation that you remember it was QG. We're going to make it one example with dry gas. Okay. So we're going to go one by one through all the parts of the system. Okay, so first we're going to go through the IPR from the formation. So if you remember, that was C times PR squared minus PWF squared to the power of n, right? Now we are go forward for the tubing, and in the tubing I'm going to show you, I'm not going to make the full derivation, but I'm just going to show you how it looks like for gas, dry gas. Okay, and that was derived by some kind of Bernoulli equation for gas. And remember that Bernoulli is based on all the pressure drop models are based on the local velocity of the fluid in the pipe, right? Also Darcy is based on the velocity of the local velocity of the fluid. Okay, so that's why we need, and the rate that we are interested is one equation that has surface conditions. So that's why we need to have some way to change between local and surface conditions. Yeah? So that's why we have all these standard conditions and the molecular weight and the R of the gas. Okay? And if you see, it depends on some other things like the friction factor, like the average deviation factor on the pipe, the average temperature of the pipe, and the length of the pipe. Okay. I can put the whole derivation on its learning if you are interested. And S is a factor that depends on the height, on the elevation of the pipe, and depends also on some other properties. But at the end, that's the equation that we are going to use. Okay, it's an equation that tells if the rate is equal to a constant times some difference in pressure, the pressure at the inlet of the pipe, pressure at the outlet of the pipe, and to the power of 0.5. Okay, so let's make those comments here. Remember, pressure drop depends on the velocity. Okay, and the velocity, if you remember, is just the Q local divided by the area, right? but we need an equations in terms of surface rates. So we need a conversion factor between local rates and surface rates. A conversion factor okay. In that case, in our case, is what we call BG, and that BG is somehow in this term and in this term, okay, and also in the set and the temperature. Okay, just that you be clear, and if you want the full derivation, you are curious to see where it came from, but that's the equation that we are going to use, this equation. The rate at standard conditions depends on two things that we can calculate, okay, depend on the geometry and depend on the drop in temperature, and relates the P in and P out. So that's the second equation we have, okay. Queuing equation is QG equal to CT P1 squared over ES minus P2 squared over 0.5. Okay, and now we have a third equation, which is the flow line equation. If you remember, now in the system we have IPR, queuing equation, and the only thing we need is it's up here, is the flow line equation. Okay, and for that I'm going to give you another equation for dry gas. For dry gas, horizontal line, you can say that Q of the gas equal to C of the flow line times P1 squared minus P2 squared to 0.5. Okay. You can actually deduct it from this equation. Now let's see if we put that, solving it. So now let's find mathematically the equilibrium rate. So let's see how many equations we have. We have the IPR equation, we have the tubing equation, and we have the pipeline equation. These are the three equations that I have. Okay, and now let's substitute the values, right? So this P1, this will be PWF, right? And P2 is going to be P wellhead. And in the flow line, P1 will be PWH, P wellhead, and P2 is going to be separator pressure, right? So let's see how many knowns and how many unknowns. The knowns, they are in red, and the unknowns, they are in blue. Okay, so let's see. C, I have it, so it should be in red. N, I have it. Let's assume I have made a test and I know how my system operates. And reservoir pressure, I have it. Bottom hole pressure, I don't have it, right? Now I continue further with that equation. So I have one equation, and actually I have, this one is also an unknown, okay? The rate, what I want to find out. So I have one equation, two unknowns. I cannot solve yet. Now with this extra equation, I know here I have one unknown that is the same that I had before, so that doesn't add much to the number of unknowns. I have the C, I have the S, I have, but these two pressures I don't have. Yes, one of those pressures I had from before, so that doesn't add much, But now I have a new pressure which had one more unknown. So how much we have so far? Two equations, three unknowns. And I go to this final equation where I don't know the rate, I know the pipeline coefficient, I don't know the wellhead pressure, but I know the separator pressure. So here I have the additional equation that I need. So here I have three equations, three unknowns. Okay, and I can solve them simultaneously to find the rate, the bottom hole pressure, and the wellhead pressure. That clear? Yes? Okay, so now I'm going to ask you, that's easy, you see the equations, but when you don't see the equations or when they are too complicated, so how do you solve it with equilibrium? Okay, let's see here, PWH, and we want to calculate the available pressure curve. So how do we calculate that curve? So let's see. We can assume a rate, okay? Assume QG. Again, we're going to assume several from 0 to QG some number, okay? QG star. Okay, in the range okay. Then in the IPR equation, calculate PWF, right? I can take this equation and I can calculate from that. I have Q, I have reservoir pressure, I have C, the back pressure exponent and the back pressure coefficient, and I can calculate the flowing bottom hole pressure, right? And now I progress, and then I say in the tubing equation, I can really, in the tubing equation, I have the rate, I have the coefficient, I have S, I have the flowing bottom hole pressure that I just calculate, and I can calculate the wellhead pressure, right? And that is the available pressure at the wellhead. Okay? In tubing equation, calculate PWH. Okay? And then repeat for other rates. Okay? So I do for 0 and all the way. So I'm going to ask you, what happens if I try with a value greater than this number? Does it exist?
Isn't it?
So this value is 0, right? So what happens if I try to use a value greater than that?
You will get a square root
Of a negative number, okay? You will get, yeah, we have to fix that equation a bit. Just copy it. Okay, let's fix it a bit. So it's Q G over CT squared, and then I get I'm clearing PWH, right, equal to the square root of PWF squared over e to the s minus that, right? So when I try a rate bigger than that, that means that it starts to be, that term starts to be higher than that term, and then it will be just undefined. Okay, which tells you, okay, I just reach, when I have 0 just, you know, vacuum pressure at the wellhead, that's the maximum rate that I can have. But really I cannot reduce the pressure more than vacuum. That is non-physical. Okay, so that's to calculate the available pressure. pressure curve. And how do I calculate the required pressure curve? Again, I assume a Q between 0 and QG star, a number that I fix arbitrarily. Then I use the flow line equation, and the flow line equation was QG CFL times P2 or P wellhead, right? Squared minus P sep squared to the 0.5. Okay. Then it says that P wellhead is equal to P sep squared plus Q over CFL square root of that, right? Yes? Okay. And that's how I obtain the required pressure curve. And the intersection is going to be my equilibrium point. Right? Okay, so now before we finalize, if that was clear, okay, now I'm going to tell you how are we going to use that to improve the prediction of the rate in every depletion stage. If you remember, okay, we had a time, we had a reservoir pressure, right? We had from the previous exercise. So what are we going to do to see how much we can produce at that particular time? Okay, with PR you have the IPR, okay, and you have the whole system. So what do you have to make? Instead of, remember what we did before, we just assume a PWF mean, right? We substitute in the IPR, that gives a rate. If the rate is high than the one that I want, I can produce. If it's low, I cannot produce, right? But what do I have to do now in base of this new tool that I gave you?
Assume Q gas.
Okay, you first find the equilibrium. What is the equilibrium rate, right? Okay. So let's say I have PR, I have a Q. For example, I can assume a Q, assumed. And then with the Q, I'm going to calculate PWF, right? Then I calculate P wellhead available. And then I calculate, then I have P sep, right? And then I calculate P wellhead required, right? So from here to here, I use the IPR, IPR. From here to here, I calculate the tubing, the TPR, the tubing performance relationship. And from here to here, I use the flow line, okay? Flow line equation, performance relationship. But then this number and this number should be the same, right? Yes? So what I'm going to make a new cell called error that will have PWH available minus PWH required. And I'm going to tell my solver, please change my QG until that value goes to 0. And that's how I calculate how much I can produce in every depletion stage. Yes? So if the rate that I obtain is higher than what I want, I can produce it. If not, then I have to use that equilibrium rate. Yeah? We don't have time to, next class I hope to make the exercise. But that's clear. Yes? That's the change on the workflow that we have done last class. Now you have to perform an equilibrium analysis. Don't stop at the bottom hole, but now you continue all the way to the separator. Yes? But let's in this time that we have available say, what does it mean to be operating? So you say, okay, Milan, you are okay, you are now giving me some, some miss signals, okay, some strange signals. You're saying that if my system is at equilibrium, that's the unique rate that the system can produce, right? Right? So how is it possible that you're saying here that I can produce a rate that is lower than that? Does it make sense? No? Let's say that's what I have at the wellhead, okay, and that's what I need. What I have is much more than what I need. That's why I try to increase the rate until what I have is exactly what I need, right? But how is another option if I want to produce that rate? That's exactly what is happening, right? That's the Q target, and that's the Q equilibrium. So how do I force that point to come here?
Use a choke.
Okay, you have to put something in between, that these pressures won't be exactly in the same place. Okay, and he said very correctly, so what you make is a trick, and actually the system is not exactly like that. Okay, so what I make is, okay, I have, so let me get rid of that. What I make is a infinitesimal space, and I say, now I'm going to put in between the available and the required, I'm going to put a choke that is going to bridge the pressure difference between these two curves. The choke is going to give me exactly that pressure difference to be sure that I'm operating at this, exactly at this rate. Yes? And that element, we didn't took it into account before. Okay? We just did like if it was, let's say it was fully open. Okay? But you can exactly say, okay, so how do we calculate, or how do we say how much the delta P of the choke has to be? If we have to say, for example, the operator, please put exactly this delta P of choke, we come to the available curve with that rate that we want. We calculate the available pressure, P wellhead available. Okay. Then we calculate with the required curve the P wellhead required, and then we subtract them, right? And then we can tell the operator, please use a delta P of exactly 30 bar, 130 bar, whatever you want. Yeah? Now that we have one more minute, I want to ask you another question. What happens if we want to have a rate higher than the equilibrium rate?
You add
Okay? In that case, the supply is much less than the demand. Okay? You don't have enough energy. So you have to use some device that will do the opposite of the choke, will boost the pressure. And for that we have to use a pump, okay? Or in our case we are talking about gas, so we have to use a compressor. Okay, remember pump is for liquid and compressor is for gas. So we have to, if we want to produce that particular rate, we have to put another element. Okay, choke is cheap. Okay, choke we have it in every well. But we have to change that element, and we have to put a pump or a compressor. Actually the symbol of the compressor is like that. Okay? And that costs money. Yeah. But if someone asks me, okay, that you can always find, the choke is a standard component, so I can achieve really any rate below the equilibrium rate by choking, no problem, it's already in place. But if you want to go to the right side of the choke, it's like going to VIP. Okay, you have to pay, and that pay is the compressor or the pump. You need to have something that will breach on the opposite direction the pressure drop. That clear? Yeah. So next class, we are going to make an exercise, and we are going to look at what happens when we don't have just one well, okay, but we have a system of wells. What do we do in that case? The equilibrium concept is still applicable. Okay? Any question before we close? No? Okay, see you next week. Okay, about the exercise, I will try to publish it by